All right, so sigma notation. Let's first talk about summation. Sigma notation, it's the Greek letter sigma, which if you've used any type of like numbers or Excel, that sigma notation will actually add up your cells. So it's like a shortcut in Excel, the program. If you hit that sigma that's up there, it actually adds up your cells, which is what sigma means as a summation. And so you have a set of terms. This sigma indicates you're going to add up the terms. And so they give you examples down at the bottom. If you had 1, 2, 3, 4, 5, 6, you would just say the sigma of this I from 1 to 6, meaning you would replace I with every element from 1 to 6, and then you would add it up. That's what the sigma piece of it means. And then like the next one, I plus 1. Well, that would mean that you start at 0. They said from 0 to 5. So if you're saying your function is I plus 1, then 0 plus 1, your first element is 1. 1 plus 1, your second element is 2, so on and so forth. J squared from 3 to 7, well, your first element's going to be 3 squared, 4 squared to 7, and so on and so forth. And so this piece of it tells you you're adding it up, and the next piece of it tells you what you're doing to it to add it up. And so that's just examples of them. There are specific types of summations that form this pattern. And that's on the next page. These patterns are on page 254. So like a constant, if I added up a constant n times, well, that's just the constant times how many times I'm adding it up. That's just multiplication. If I'm just adding up numbers like from 1 to 100, this is the story told of Gauss being the mathematician from like, I don't know, 1600s, somewhere in there. I feel like I need to look it up. When he was in elementary school, the story is told that his teacher got upset with the class and said, all right, add up the numbers from 1 to 100. And they started adding them up, 1 plus 2 plus 3. Within a minute or two, Gauss came up to the teacher's desk and gave her 5,050, which was the correct answer because he had seen a pattern. And so this pattern is attributed to Gauss, saying that he came up with it when he was at a young elementary age. And so this is just saying if you take the total number that you're going to add up, divide by 2, and then multiply it by 1 more than that, you get your summation. Which if you look at from 1 to 100, 1 to 100, if you did something like this, you would say that all of your groups add up to 101. That's your n plus 1. Well, if you have 1 to 100 and you pair up the groups, you're going to have 50 groups, which is your n over 2. And that's how he came up with that particular formula. There, as adding up 1 to 100, what if you added up the squares? 1 squared plus 2 squared plus 3 squared plus 4 squared. That also creates a pattern. You can take, let's say we were doing that to 100. 100 plus 100 plus 1 plus 2 times 100 plus 1 over 6, and you will get the summation of 1 to 100 squaring each number. Cubed, same thing. However many you have squared, 1 more than that squared over 4. And so these are some somewhat special case summations that you want to memorize here. These you need to memorize. So let's look at how we do that. How do we apply those summations? Look at example 2 here. All right, so we have the summation of I from 1 to n of I plus 1 over n squared. N squared is considered a constant. So when it's like this, it can actually be pulled out. So you can take the 1 over n squared out here, and you have the summation from 1 to n of I plus 1. These are 2 summations we have up here. We have the summation I, well, that's right there. So we're going to replace that summation with this guy. And then we have the summation of a constant, well, that's here, and we're going to replace them with that guy. So we literally just plug those in. So I would say then that's going to equal 1 over n squared. And then I'm going to replace this whole summation with the summation of each one. All right, so I'm going to replace the I with n plus 1 over 2. And I'm going to replace the constant with the constant times n. And then you want to simplify it as much as possible. So you want to distribute here, right? So we have n squared plus n over 2 plus, and then we want a common denominator here. So multiply top and bottom by 2. 2n over 2. That way we can combine those guys, right? Which gives us then n squared plus 3n all over, and we're going to multiply this by our common denominator, 2n squared. And then what do you think I can do there? Yeah, take an n out. So I have n plus 3 over 2n. How does this help me? Well, if I wanted to add up all, for, let's say my n was 100. Well, instead of saying 1 over 100 squared plus 1 plus 1 plus 2 plus 1 plus 3 plus 1, like from that to 100, that's not fun. When you put it in this form and simplify it, I can actually just take this guy that I simplified it to and plug 100 in. 100 plus 3 over 2 times 100. And so I can see my summation of what it would be if I did that. Instead of adding up each one, I can simplify my summation itself and then plug it in, which makes it much nicer. So then the tangent line problem was the first thing that they ran into, which is where we kind of came up with derivative slope of the tangent line, and we went from there. And then the next problem they found is that area was not as easy as it seems. In pre-calculus, you have area of definite figures, rectangles, squares, circles, etc. But then when you get into the real world, you find that very few things come in squares, rectangles, and circles perfectly. You have curves. And so they came upon a curve and they're like, oh, how do I find the area under a curve? Because this is not a specifically defined geometric figure. And so they started with, well, let's start with what we know. We know rectangles. And so what happens then if we put rectangles here? Well, I'm going to get a somewhat of a close estimate here. But you'll notice that the area of the rectangles does not include some of the area here when it's under. So if I start at the 0 and that's my starting point, I have some extra that I didn't count. Well, if I use my height based on the y value across here, well, I have too much. And so what they found was it's somewhere in between, right? So if I have on the left side, if I have these guys, and on the right side I have these guys, I know my actual area is going to be somewhere in between them. And so this is how they started calculating this. The first thing you have to look at is the function they gave you itself. The function they gave you is negative x squared plus 5. Well, what do they want it in between? Well, they want it in between 0 and 2. And so they want the area of this function in between 0 and 2. And so they said, well, how many rectangles do you want? And so right now it says use 5 rectangles. Well, there's 2 ways to use it. I can use 5 rectangles starting here. My y value is my value at 0. My x value is the width of the rectangle. And then I do one more rectangle. My y value is this guy, width, this guy, width. Or I can do it this way, and this is my y value, my height and my width, my height and my width. And so we're going to start with this guy, left endpoints, left endpoints. So in this case, and actually I think this is right endpoints, left endpoints, it's on the back, it's backwards. Visually it's left, but it's the right endpoints. So how do I figure out what those endpoints are? Well, I take my total amount, so I'm going to say from 2 to 0, b minus a, right? All over how many rectangles I want, all right? All over the number of rectangles. So I'm just going to say b minus a all over the number of rectangles. That's going to give me my width, all right? In this case, my width is 2/5, all right? And so you basically start at 0, and you walk 2/5. So my first endpoint is going to be 2/5, and 4/5, then 6/5, then 8/5, then 10/5, which is 2. All right. And so you have these groupings then of rectangles. That's your width. Your width will always be 2/5 for this guy, always. And so if I'm calculating the area of the rectangle, how do I calculate it? Where I calculate it, the height times the width, right? Height times the width. Well, I just found the width of every single one of my rectangles. All right? So then the question says, well, how do I find the height? How do I find the height? Well, it depends on where you are. I'm going to take that 2/5 and I'm going to have to multiply it by where I am in the function. That's going to be my x value that I plug in. So my x value for my first endpoint is going to be 2/5. But the second endpoint is going to be 4. So it's going to constantly be changing. And I want to add up all of my rectangles. Well, that is a summation problem. But now we have a summation problem with a function itself. And so I'm going to say, well, I definitely want to add up all of my rectangles. That's where I get my summation guy from, right? I know that I'm going to have 5 rectangles. So I'm going to start at 1 to 5. Those are my walking steps there. But how do I find my height? Well, I'm going to take my function, f of the x value, wherever I am, right? So the x value, wherever I am, that's going to be my y value. Plug it in. Well, what is your x value? Well, it's going to be your width times I, whatever step you're on. If you're on the first step, it's going to be 2/5. Second step, 4/5. It's going to be 2/5 times your I, whatever step you're on. So your width, basically, times your I there. And then you're going to multiply that guy by your width itself. So this piece represents the height, and this piece represents the width. All right? Now we actually have to take this and plug it into our function. Plug it into our function. So I'm going to say, well, I'm going to do the summation then from 1 to 5. And now I'm going to say f of this guy. Well, if I'm doing negative x squared, negative, this is my x, 2i over 5 squared plus 5. That's my height, right? And my width here is 2/5. All right. Now, keep in mind that 2/5 can actually come out, right? And so sometimes they'll pull it out. They'll do the summation first and then they'll pull it out. So how then do I calculate my summation here? Well, I can take this guy and I can put him in front. So the 2/5 can go up here. Here I have, and actually the negative is going to be after you do your I. But this is 4i squared over 25, right? 4i squared over 25. Does that make sense? Because I'm going to square those. So we have 4 over 25. What is my I squared? We'll go back to your summation. Summation on page 254. What is I squared on page 254? Well, it is n plus 1, 2n plus 1 over 6, right? So I'm going to replace the I squared with n plus 1, 2n plus 1, all over 6. And then I'm going to add to it my constant, which is just 5 times n. All right, so far so good? I will say, when you're doing it with an actual number here, you can just plug in a 5 if it would be easier than simplifying. So it just depends on what you're trying to do. So if I have a 5 there, I can actually go ahead and plug a 5 in here, if that would be easier, right? If you're trying to do it for multiple ones, like I want it for 5 and for 10 and for 15, you want to simplify it all the way down. But here, if I'm just doing this to save myself potential foiling problems, right, which is very, very possible, then you could just say, you know what, I'm going to stop right here and I'm going to plug a 5 in. This is going to be 5, this is going to be 6, that's going to be 11. Does that make sense? And so instead of potentially messing up, you can stop right here and do it like that. Which means that you can then, and I actually already had my 2/5 at the beginning, so I can erase this guy, which means that you can simplify him a little bit. You can say, okay, well, the 6s can cancel there, right? And the 5s can cancel here with a 25. And then I have negative 4 times 11. So I have 2/5 negative 44 over just a 5 here plus 25. And so keep in mind you're doing common denominator. So 25 over 1 is going to be what? 125 over 5, right? Make sense? And then simplify this a little bit. And I think they actually get a decimal, but 125 minus 44 times 2. And then we're going to multiply this through. So we should get 162 over 25, hopefully, if I did my math. Get 162 over 25. And when they put it in decimal form, 6.48. All right? Questions on that? When they use left endpoints, so I always use right endpoints because unless it tells you have to use both, which I don't know. So if I were to do it the other way, so let's say I'm still going to have the same width, right? But instead of just 2i over 5, you actually have 2i minus 2 over 5 because you're actually going this direction. So you're going to go 2i minus 2 is going to put us all the way at 0. 2i, the next one, minus 2 is going to put us here, then minus here, then minus. So when you're doing the right endpoints here, or rather the left endpoints, you actually subtract your endpoint from it. So you're actually going the other direction. But it basically gives you, they have, when they do the other way, get 8.08. So somewhere in between there is going to be your actual. You'll notice if you look at the graphic then on the bottom of page 257, what you start seeing is, just like we did on the first example, we got 6.48. If you do the upper ones, you get 8.08. somewhere in between that is my correct one. We did it with only 5. Here they did it with more. 1, 2, 3, 4, like I think 8 or 9. I don't know how many they did here. So you'll see that there's less area underneath the curve, less area above the curve, right? And what actually happens is the more rectangles you have, the closer you get to the actual area of the curve, which is where we actually get, like in this case, they only used 4. You'll see you had a pretty good chunk left underneath it, a pretty good chunk above it, right? And so what starts to happen is what if I had 50? What if I had 100? And then you would say, well, what if I had an infinite number of rectangles? Well, if you have an infinite number of rectangles, you actually have the actual area under the curve. And so you move towards an infinite mind. Well, how can you do an infinite number of rectangles? You can't calculate the width and the height for an infinite number of rectangles. That's not logical. So if you look at page 259 then, what you actually do is you use limit theory. So you can then use your summation to come up with the function itself, and then you can use what happens as my n approaches infinity here. Then what happens? Well, then you actually move towards the actual area under the curve. And so we can combine what we know about summation notation and what we know about limit theory as n approaches infinity, and we can actually calculate the area here. And so this is the definition. The area is going to equal the limit as n approaches infinity from 1 to n of f of c of I delta x, all right? Delta x, how my x is changing. So let's look at this applied. It says, find the area of the region bounded by the graph f of x equals x cubed, the x-axis and the vertical lines 0 and 1. All right, so basically what they're telling us is, well, we want you to go from 0 to 1. I'm still going to say b minus a. So I have b is 1, a is 0, right? So I'm still going to say b minus a over the number of partitions that I have. But my number is going to be infinity. So I'm going to leave it as an n right now, okay? In this case, my b is 1 and my a is 0. So my width here for all of my things is going to be 1 over n. All right? I'm going to take that width and I'm going to multiply it by I, because it depends on which step I'm on. And that's what I'm going to plug in. So here is my width here. My x value to plug into my function is going to be this width times I. All right? So what I'm going to plug into my function then is I over n. So I over n is what I'm going to put into f. All right, well, what is my f? My f is x cubed. They gave that to me. So I'm going to say, well, the limit then, as n approaches infinity, of the summation from starting with 1, I equals 1 to n, of my function. Well, my function is going to be I over n plugged into my function is I over n cubed, right? Times my width, well, that's 1 over n. All right, so first of all, remember 1 over n, that's just a number that I can pull out in front. I actually have, if I know this to be true, right, so this is going to simplify to I cubed over n cubed times 1 over n. So this is going to be I cubed over n to the 4th, right? I can pull the 1 over n to the 4th out here, out in front. So I have my limit as n approaches infinity of 1 over n to the 4th, summation then of I cubed. What is the summation of I cubed?
It is n squared times n plus 1 squared divided by 4.
Yep. And then on the outside, I still have 1 over n to the 4th, and I still have my limit. Now, you do want to simplify this before you apply your limit theory, okay? So we are going to simplify this. We're going to FOIL that. So that's going to be n squared plus 2n plus 1, right? Multiplied by n squared. Distribute that through. N to the 4th plus 2n cubed plus n squared over, and these two just multiply, 4n squared. All right? All right, so what do you think we can do here? Can't we? So let's simplify it a little. Let's split it up. Let's split it up. We have n to the 4th over 4n squared, right? Plus 2n cubed over 4n squared plus n squared over 4n squared. So far, so good? All right. Let's do my limit theory. What are my infinite limits? They're my shortcuts, aren't they? Yes? Right. Right. So, and I think, right, am I wrong here? This should be into the 4th. This guy is into the 4th. I should have written a 4 there. That's a 4. That's a 4. That's a 4. So far, so good. All right, so this one, denominator on bottom is bigger. What's that going to go to?
Oh, it's going to go to 0.
This guy, what's he going to go to?
0.
0. This guy, what's he going to go to? 1/4. All right. Same thing would have happened if I had done it up here, even if it's not simplified, but they show it in the book simplified. My degree on the bottom is 4. My degree on the top is 4. I use my coefficients. So this whole area is going to be 1/4. The area under the curve is 1/4. Limit theory. All right. Your width is still going to be, so this is from 1 to 2. So your delta x is still going to be your 2 minus 1, which is 1 over n. That's still going to be your delta x. But all of a sudden, you have to bump over what you were doing. So your function here is 4 minus x squared. Well, your x squared is not just going to be your delta x plugged in times I. You have to add a 1 to it because you're starting at 1 now. So we're going to say, we're going to plug in here 1 plus my delta x times I over n, right? And that's what we're going to plug into the x. So it's going to look like this for my function. And my width is still going to be 1 over n. But now we're going to have this a little bit crazier thing going on here. So when you start not at 0, you have to consider the fact that your graph has just bumped. And same true if you were to go the other direction, -1, you would just say -1 plus because you're bumping the other direction. Does that make sense? So the example we did before started at 0, no big deal. Now you have to consider what, so basically what we did before was 0 plus delta x times I plugged in. Well, 0 plus that doesn't really matter. But when you do move somewhere off the graph, it does. And you can see it's going to change it considerably. I mean, this is going to be a much more difficult one. Not difficult, tedious, really. I mean, it's not that it's hard, but now when I figure this out, I'm going to have to FOIL this guy to figure it out. And you'll see, once again, you're going to end up with something rather simple. It's going to simplify to, you know, the 3 minus the 1 minus the 1/3 at the bottom. But the process by which you do that, you have to FOIL this here. And then you have to consider, you can still pull this 1 over n out to be up here at the front, right? But you do have to FOIL it. So you're going to end up with something like 1 plus 2i over n plus I squared over n squared here in your summation. And so it's a little bit more difficult and a lot more room for error, as you can see. But you would just replace your I squareds with what they are. Make sure you don't forget to put him through after you do your summation replacements and use your limit theory at the very end. And it ends up being fairly straightforward. I mean, this guy simplifies to a -1. This guy's going to simplify to a -1/3. It ends up just being 5/3. Nothing hard as far as the numbers themselves, but pay attention to your foiling. Pay attention especially here that when you do this, you distribute that negative through. That if you don't, you're going to end up with a different number there. And so make sure you distribute that negative through, which is how you end up with a negative and a negative here, is by the distribution of that -1.